Okay, so last week we talked about this sort of framework for reinforcement learning, including an interaction between an agent and an environment. And then the plan for today to talk about what it means to learn in this framework. So the topic for today is learnability. So to talk about learnability, we need something to evaluate the agent against, and typically this would be some form of a utility function. And then kind of a general form of a utility function in reinforcement learning would be something that takes a destiny, so an infinite sequence of observations and actions, and outputs a real number, going to restrict to 0, 1 for kind of technical convenience. So this basically takes in a destiny, so like here's how everything played out until the end of time, and then based on that, it outputs a number of like, okay, how good was this? So this is a kind of a general form of utility function, but in RL specifically, a utility function usually comes from something called a reward. So we can, I guess a general form would be a history-based reward function, which takes in a history of observations and actions. So this is a finite string of these. And I call this R, and outputs a real number in the interval. So this basically is sort of a, it sort of says, okay, here's what happened so far, how much reward is associated to what has happened. And a special case of this would be, which I think is commonly but not always assumed, is the special case would be right. So the utility function takes a whole destiny. So it's sort of like everything that happened, and okay, in a few minutes we'll see how to get a utility function out of a reward function, and I think it will make sense what the kind of fundamental difference is. But first I want to say a special case is when the reward is directly observed. So this would mean that I guess one way to think about it is it's a special form of this history-based utility function, which basically factors through the last observation. So if we just project out to what we last observed, then if the reward is of the form where there's some R tilde here, which just basically we observe something and kind of part of that observation is what the reward is. So this is it can be thought of as the reward being directly observed. Even sometimes people write the observation being equal to like the reward itself times a sort of side observation. So like you observe the reward and maybe that the sky is blue. So you can think of this R tilde as just a projection onto the observed reward. Okay, so this is a reward, and I guess I was going to say, so if you have a reward, you can construct a utility function out of it, and for that, just a quick quick notation is that if you have a destiny D, which is an infinite sequence of observations and actions, you're right. D sub colon T for the restriction onto the first T coordinates. I guess maybe I should ask if there's any questions about this first page. So this is just some notation. We'll write this D sub T for the part of the destiny that is the first T time steps. And then, so using this notation, we can construct a utility out of a reward function. And there's a few ways to do this. So two typical ones would be to restrict a finite time horizon, T. So this is a natural number. And then we can say that the utility up to this time horizon T of a certain destiny D, this is just, we can define it to be the average reward received. This is for T. So basically, this gives a sort of high-level idea of how to turn a reward into a utility function, namely, you average the reward.
What are we summing over?
Yeah, okay, I guess maybe I could write T equals 0 to T minus 1 instead here. I guess sometimes you can think of a number as just the list of indices of that number. So I wrote little t and capital T, but maybe this is clear.
So this is something like we are constructing a utility function over infinite trajectories, but only the first capital T elements of this trajectory matter.
Yeah, but then I guess in general we're gonna care about the T goes to infinity limit. So yeah. Maybe I'll so this is one way to do it, is to restrict a certain finite time horizon and then average over this finite many time steps. And then another common way to do it is to use a geometric discount. So this would be with a discount factor gamma, which is in 0, 1 not included. So here the corresponding gamma discounted utility would be it's sort of also like an average, but a kind of a geometric average of yes, here we take gamma to the T R of D up to T, and here we can sum over equals 0 to infinity. So these are kind of two ways of averaging, and I guess as Mateusz was asking, like, okay, so we restrict a finite time or a certain discount, but I guess we often care about the limits as T goes to infinity, or the analogous thing is to gamma goes to 1. So that's when we the discount goes to like basically having close to no discount. So these are the sort of two typical ways of turning a reward function into a utility function. Of course, you could use other forms of summing things up, and sometimes those could be useful as well, but I think these are the most commonly occurring ones. And they're actually like, they behave pretty similarly in practice. So I think going forward, I'm going to use the restrictive finite time horizon notation, but everything I say, I think, can be directly translated to geometric discount, and the behavior is often very similar, except in maybe some pathological cases. Okay, any questions about this slide?
And the reason we have 1 minus gamma is to make sure we're within 0 to 0, 1 interval.
Yeah, it's sort of the normalizing factor, like the same as the 1 over t or the 1 minus gamma. It kind of makes it into more like an average-like quantity.
Okay.
Okay. Any other questions?
Yeah, I have a question. If both limits exist, are they always equal?
That is a good question. My guess would be yes, but it's a good exercise to try to work it out. Yeah. No analysis or exercise. Okay, so these are rewards, and then we have a way of turning them into a utility. And then, okay, so given a utility, we can talk about the kind of expected utility. So if we have given an environment eta, what did I call this? A stochastic environment in ES, and policy pi can also be stochastic. I guess last week we talked about this interaction between them, which gives us a distribution over destinies. So putting this together with the utility function, we can talk about the expected utility with respect to the distribution that is this interaction of the utility function. So I guess the utility function being a function on destinies. I guess assuming this exists, I'm generally going to probably skip over technicalities. Like often this utility function is required to be continuous, which means that kind of as you go off to infinity, those factors are required to contribute so less and less as a kind of a high level hand wavy characterization. But yeah, I think we're not going to worry about that for now. Just assume that this exists. Okay, so that we can talk about this expected utility, and then using this we can say for a fixed environment eta, we can talk about we call it U star U star of eta, which is the optimal expected utility under this environment. So it would be defined as a supremum over all policies of the expected utility under the interaction. So this is the optimal utility for that environment.
And because you use supremum, does that mean it's not always sort of realized by a specific policy?
Yeah, so I guess, yeah, here, okay, here's where the kind of technicalities come in. If you assume the utility is continuous, then we can replace this with a maximum because the space of policies is compact. And so here we have a continuous map from a compact space, so the supremum will be obtained. But so I guess for that regard, it's useful to assume the utility is continuous. And by the way, if you take u equals to ut or u gamma, these are going to be, I think by construction, these are going to be continuous. Okay, does that make sense? Here's a question in the chat. Could you read out the question? It just disappeared.
Yeah, I mean, my question is like, how does U star, like this highest utility that can be obtained in eta for any by any stochastic policy, how is it related to the decision estimation coefficient? Because from what I've heard from Alex, Diffractor, it's something like the best any policy can do in any given environment, or at least like that's one thing that it can be interpreted as.
Right. If you can remember this question, I think it would probably be better to ask towards the end, for the discussion part, because I think by then we'll be in a little better position to say what kind of thing is the decision estimation coefficient.
Okay.
Because I think for that we need a few more definitions. Any other questions about this? Okay, so using this previous definition, we can for an environment eta and the policy pi, we can define the regrets, the regrets of this policy with respect to this environment. This is not symmetric. So this is defined to be the optimal utility. Maybe I should say. I guess this also depends on the utility. So this is the optimal utility for the given environment minus the expected utility for this specific policy. So this is basically saying how much worse is this policy doing than the optimal policy. So that's the notion of regrets, and we can define a hypothesis class which we would just take to be a subset of environments. So this, I guess we'll encounter this a lot. I guess generally, like when talking about an agent learning something, it's always going to be with respect to a certain hypothesis class. So these are the hypotheses of possible environments that we consider. So given a hypothesis class H, we can say that the policy pi learns the hypothesis class H if the regrets. So here we're going to use the this is going to be for a utility defined for a reward, certain reward function. So I'll write u sub t here. So if this goes to 0 as t goes to infinity for all environments in the hypothesis class. So this is going to be key definition for going forwards. So maybe we can pause for a minute to kind of digest it and ponder over it. So I guess why is this a reasonable definition of learning? So suppose its limit was not 0. That basically meant that it basically means that there's there's going to be a certain fraction of times when the policy does something wrong. So basically, let's say your policy is trying to classify cats and dogs, and then you end up with a regret that stays above 10%. That means basically roughly 10% of the time your policy gets cat versus dog wrong, which basically we cannot say that it fully figured out what cats and dogs are. So if this goes to 0, this is it's basically sort of a weakest possible condition you can put on something to be able to say that the policy actually learned what's going on, namely kind of in the limit, it gets the most reward at each time step. So it basically eventually figured out the right thing.
So in machine learning, we would often think of a policy as being the result of a learning process. But here, policy is not separated from learning.
Right. So I guess that is a good point, which I haven't talked about, or maybe I mentioned it briefly. There's so maybe that's actually a good thing to go into a little bit. I think we have the time. So we can talk about, what did I do? We can talk about a distinction between lifetime learning versus episodic learning. So lifetime learning is the setting I've been working in so far, because I think it's notationally just a little simpler. That's the main reason. In episodic learning, we basically only consider environments and policies up to a certain episode length t. So with the episode length t, so we only consider both the environments and the policies are up to just a finite episode length. And then we imagine the kind of learning process by running an episode and then restarting the whole thing and trying again. So it actually turns out to be a special case of lifetime learning, where you just, except that it has this special feature that the environment restarts after each t time steps. So in that case, the kind of learned policy would be kind of this part of it, but the learning algorithm itself runs across policies. So it is sort of, in that way, sort of a lifetime algorithm. So hopefully that clarifies that.
Yeah, very helpful. Thanks.
Can you repeat the last part?
So yeah, basically, so in lifetime learning, you can imagine basically kind of just you get an observation, action, and it keeps going forever. And then the policy just kind of needs to figure out what to do on the fly. So like there's no resets basically. There's really one way to characterize it. In the episodic learning, we basically have a fixed episode length. So we run the environment and the policy for t time steps, and then reset everything to the beginning and do that again. So basically, keep going like this. So we just run the episode of time t up to time t again and again. So in this sense, basically, it's a special case of the lifetime learning, where we basically just keep going on forever, except that it's broken into these reset chunks.
But the policy isn't reset, or is it?
Well, okay, so yeah, I guess I didn't go into detail. So we can talk about in this case, we can kind of talk about the learning policy, which basically takes into account what has happened in each episode so far, and then outputs a policy, let's say, for the next episode. So there's kind of a sort of an output episode policy. So basically, the learning policy looks at what happened so far in the previous episodes, and then based on that, comes up with a new policy for the new episode. And then Koshin was asking, like, okay, so, and then this is what ends up being it's a finite time learned policy that the learning algorithm outputs that operates on the episode itself.
Okay, I think that's clear. Yeah, thank you.
I guess another way to think about this, which is a little more abstract but maybe helpful to some people, is you can think of a new set of actions, which are basically the policies of the episode. And then basically the kind of learning policy outputs an action in this big action set, which will be specifically the policy for the episode. That's either helpful or confusing. But if it's
that's actually that's actually what I thought of. So yeah, that's good.
okay. Yeah.
Thank you.
Okay. Were there other questions? You can treat this as more of an aside, because I think for this course, we'll at least up to week 5, will definitely be mostly just dealing in the lifetime learning setting, because I think it's conceptually a little easier, but it is good to clarify that in practice, when like, an oral agent is learning like an Atari game or something, it is in the episodic learning setting where you like reset the game at certain points and then break it into episodes in that way. But I guess maybe one thing worth mentioning is that if you imagine kind of letting an agent run loose in the world, then maybe it's better to think in terms of lifetime learning, because there's not really a reset button in the real world. So in that way, I think it's helpful to keep the lifetime setting in mind. Okay. So as I said, this is our key definition of what it means for something to learn. And I guess here, so maybe I should say I cheated a little bit just to make it conceptual simple. What I wrote down is a definition of anytime learning. This is saying pi learns h anytime, and there's a more general definition which is often considered that a family of policies pi sub t. So here we allow the policy to depend on the time horizon. So this family is set to learn a hypothesis class, and is the same definition if the regrets of pi with respect to eta and u goes to 0. Yes, t goes to infinity for all eta and eta in h. So this is basically a little bit of a weaker definition where we allow the policy to depend on the time horizon. It should be ut. And then the anytime learning is a stronger property where the policy is independent of the time horizon.
Then I think it should be reg pi t.
Yeah, right. Yeah, thank you. And then I guess another definition that's worth mentioning is just that I write this for the anytime case just because the notation is simpler. Learns h uniformly, and I guess anytime because I didn't write the t. If we have the supremum over the environments of the regrets of pi with respect to eta and u t, the supremum goes to 0 as t goes to 0 after t goes to infinity. So this again is a stronger condition where we require the regret to kind of uniformly converge to 0.
At this stage, we don't know if such a pi exists. Is that right?
Sorry, what's the question?
We don't know if pi
If pi exists.
pi that learns exists. These are just
Yeah, right. So yeah, actually, that's a perfectly way into the next definition that they say that the hypothesis class H is learnable. I guess anytime learnable is the. If there exists a pi that learns H. So it's sort of it's a simple definition, but yeah, basically it's a good point that some hypothesis classes are not learnable. So we say that it's learnable or anytime learnable or uniformly learnable or anytime uniformly learnable if the kind of corresponding definitions, or if there exists a policy for which the corresponding learning holds. Yeah, and then I guess maybe I should say, part of an interesting thing in AI theory or learning theory in general is to understand like what kind of classes are learnable and I guess the bigger a hypothesis class, the less likely it is to be learnable. So basically, an interesting thing is to kind of try to find a sweet spot of a hypothesis class that's like large enough to still be learnable, but kind of rich enough to capture capture a lot of possible environments.
This property is preserved under like taking subsets of H, right?
Yes.
Is it also preserved under finite union?
That is a good question.
I think it shouldn't,
Yeah.
because you can have a bad environment that traps you if you start with a bad action.
Right. Yeah. Actually. Yeah. It's not gonna be closed under finite unions. Here's an example. So let's say we have two actions, A and B. And let's say there's just two things that can happen. If you take action A, you end up in heaven. You take action B, you end up in hell forever. So once you're there, whatever you do, you're stuck there. So this is one environment, eta 1. So this hypothesis class of just this one environment is learnable. Namely, you just take action A, and then take whatever else afterwards. So let's say this is one hypothesis class, and then take another hypothesis class, which is the same setting except A and B are switched. So now B takes you to heaven, and A takes you to hell. And then again, you're stuck there afterwards. Let's say this is eta 2, then if we take H2 to be just eta 2 in itself, that's also learnable. So here we have H1 and H2 are learnable, but H1 union H2 is not. Because once you take the union, the optimal policies are going to be very different, because for one, the first step needs to be A, for the other one, first step needs to be B, and there's no way to recover from that. So
Okay, I see. Yeah, thank you.
yeah, that's a good question. Okay, so this is learnability, and I guess I wanted to say kind of a general thing that, as I mentioned here, this sort of converging to zero is sort of the weakest possible condition that we can have on to capture learning. But in practice, what often happens is that the rate of convergence to zero is an interesting parameter of the hypothesis class. So I guess interesting. Maybe we could say it's an interesting measure of difficulty of the hypothesis class. So I guess so far this was in the abstract, but in practice, kind of understanding a hypothesis class often involves proving certain regret bounds. So this can be, in general, upper bounds or lower bounds. So we're going to see some examples of these in the upcoming weeks. But as just kind of a made-up example, let's say and upper bounds are usually, proven by construction. So if you can construct a certain learning algorithm which attains a certain bound, then you have an upper bound under regret. So this would look like construct a learning algorithm but a learning algorithm is basically just a term for a policy which learns a certain hypothesis class. This would be constructing a certain learning algorithm pi and showing, for example, that the regret up to time t of that pi across this hypothesis class is maybe you can show something like it's O of 1 over square root of t, for example. That would be one kind of regret bound you can show. So that would be a certain bound on the rate of convergence on how fast regret goes to 0. And then the lower bounds they often involve like actually understanding something about the structure of the hypothesis class. So in that case, you might prove something like that for the same problem, the regret up to time t of any policy is always bigger or equal than what's the notation? Oh my god, is that a thing? Let's say t to the so it's some constant times t to the minus 2/3, for example. So, and an interesting thing is to try to make the lower bounds and the upper bounds kind of match up with each other. So yeah, okay. These are just completely made up examples, but maybe it gives a sense of like what kind of things you can try to prove about a hypothesis class. Okay, any questions?
In the lower bound, we want to show that for every pi, right?
Mm-hmm. Yeah, so that would be for all pi. So this can be sometimes tricky to prove because there can be a lot of different learning algorithms. So showing that no learning algorithm can do better than something can often be tricky. But it's actually often it gives you some insight into the nature of the hypothesis class. So this can be good things to work out too.
So I'm guessing for like a simple problem like multi-on bandits, they have a pretty good lower bounds.
Right. Yeah. So I guess next week we'll introduce the kind of I guess it could reasonably be called the simplest possible setting for reinforcement learning, which is multi-on bandits. So that will make things a lot more concrete, and then we'll see. We'll work out some examples of how to show an upper bound and what kind of lower bounds exist. Okay. So I guess one thing to note is that our definition of learning, it involved this, that has to be true for all hypotheses. So because of this is sometimes called a frequentist, frequentist guarantee on the the algorithm. But it makes sense to talk about these definitions in a sort of in a Bayesian setting too. So we'll look into that quickly. So given a prior, let's call it psi over a hypothesis H. I guess we can talk about the expected so we saw how if you have an environment eta and a policy pi, we can take the expected utility. So let's assume you have a utility function u. We can talk about the expected utility coming from the interaction of that environment and the policy. And then if we have a prior over the environments, then we can take the expected value while sampling the environment from the prior psi. And so this would be kind of the expected utility under certain policy given our prior. And then using this notion, we can talk about Bayes optimal policies. So we write this as say pi star psi. I guess it also depends on you. Sorry, I'm not super consistent of what I put as superscripts or in square brackets, but these are just kind of notations for the time being. If you're writing something, you can maybe omit some of these. So this will be something, I guess technically I should write. It's an element in argmax over policies of the expected utility across all the environments sampled across according to this prior xi. So this is a kind of an optimal learning algorithm given this prior. But of course, it's like in practice, it's almost always impossible to compute at all. And then maybe it's worth mentioning a famous example of this. If you take H to be the class of all computable environments, so this is a fairly big class of environments because there are a lot of computer programs, and we can take our prior xi to be it's called Solomonov prior. So this is basically something that's I guess xi of a environment eta is some function of the description length of eta. I guess maybe you want to take something like 2 to the minus k to the eta, but I guess it's maybe put a 2 here. I guess you can choose a function for which you get a distribution. And so in this case, the Bayes optimal policy with respect to some utility function u is what's often called AIXI of that utility function, or I guess sometimes just called IXI. Okay, so this is one example of a Bayes optimal policy with respect to a certain big class of environments and a certain prior.
So what was the notation on the final line?
The notation.
Yeah, I'm getting mixed up with the AI. Is that an I or is that a vertical line?
It's a AIXI. So XI is our prior,
Yep.
which is some kind of Solomonov-like prior, and then I guess this is AI. Okay, this is just what it's called, but I guess it's often referred to as IXI, just spelling out the XI, the letter XI as a XI.
Oh, I see. Right. Okay.
And then, yeah, I guess so we define the Bayesian version of the expected utility, and we can also define a Bayesian regret, which would be analogous, but yeah, I think. Yeah. Okay, maybe I'll write it out for sake of record. Bayesian regrets with respect to the prior XI. It's going to be it is BREG I with respect to eta U psi. So this is going to be the I guess the optimal expected optimal expected wait, sorry. Okay, okay, sorry. I think this is just defined as the expected regret when sampling the environment from the prior. So, I think this is a meaningful definition. Sorry, I didn't check this definition, but I think this is the right definition of Bayesian regret. Okay, I guess we're close to time. So, any questions about anything we talked about today?
If there's other questions, Google Glass asked half an hour ago whether the motivation for both T and gamma versions of how to get a utility function from the reward function. Is it both to get the closest thing possible to a uniform distribution over natural numbers?
Oh yeah, right. So I guess yeah. So one thing we could do is to skip over the gamma or take a finite time horizon, and we could. I guess one thing we could try to do is to just take a limit as t goes to infinity of the average reward. But I guess this limit doesn't necessarily exist in general. So another thing you could take like lim, for example, the worst worst average in the limit. And I think that would be fine probably if you use just this lim. Define u of d to be this. That would also be fine. So you could work with that. I guess for learnability, we do let's see. Yeah, I guess. Yeah, it would probably be fine to just say something is learnable if this utility converges to the optimal utility for a certain policy. So yeah, you could use this kind of definition too. I think it's often in practice helpful to look at things in like at a finite stage and then like argue at a certain finite time or a finite discount factor, and then say what happens in the limit rather than just trying to immediately jump to the limit. But yeah, I guess you could just start from here if you wanted, I think. Does that answer the question? Okay, so yeah, we're at time. If people need to go, feel free to go, and we can yeah, I guess stick around for a few minutes if there are any other kind of more general questions. We can, I guess, return to Matej's question about decision estimation coefficient if unless there's some more pressing questions.
Are you asking me to repeat the question? Or
yeah, or I guess I can try to paraphrase what I understood the question to be. Or I guess
Yeah,
you were
sure.
asking maybe. I think basically you were asking how does the deck or the yeah, maybe I should write this out. So there's something called DEC, which stands for decision estimation coefficient. So this, yeah, basically this can be thought of as a sort of certain dimension or certain measure of learnability for a certain class of environments. So yeah, maybe I can describe a simpler setting. Is let's say one thing we could do is, and we'll come back to this. So maybe I'll just describe things on a high level now, and then I think in week 4 I was planning to come back to this. So let's say we could take the hypothesis class to be the set of MDPs of diameter less or equal to some number d.
what's the diameter of an MDP?
Yeah, so I think I won't spell out the exact definition right now, but I think I probably will in week 4. But to give you an intuition, so like basically an MDP has a number of states, you know, and certain transition probabilities, like let's say taking action A, there's 20% probability of going from here to here. And then maybe taking action B, there's 10% probability of going from here to here. So if you pick out 2 states in an MDP, you can ask like, how long does it take an expectation to get from one state to the other if you like follow the best policy you can to get from here to there. And the diameter is basically the biggest possible time it can take go from one state to another. So that's kind of the high level idea. In particular, if your MDP is split into two parts which are not connected at all, like these are connected amongst themselves, but these are connected amongst themselves, but if two are not connected, then the diameter would be infinite, as you said. So having a finite diameter means that the MDP is strongly connected as a directed graph. And then the diameter measures kind of like how long does it take to get between the two sort of furthest points. So if you take this hypothesis class, then we can prove certain regret bounds. We can prove that the regrets, I guess these are uniform bounds, and we can prove that so that's equal to something like maybe the square root of d times, I forget which ones go under the square root and which ones don't, but maybe I'll look this up when we actually talk about this. But let's say something like this. So maybe this is and there's probably some constant in front of it.
And this is for any policy whatsoever?
Yeah, so you can, well, no, this is, sorry, this is saying that
there exists a policy that has
there exists a policy for which to regret. But yeah, as I talked about earlier, the upper bounds for regret are existence results. And then you can also, prove a lower bound saying that for all policies, the regret is bigger or equal to some other thing. And yeah, these are things that, that change over time. People like actually still improve these bounds to this day. But yeah, in week 4, we'll come back to this and talk about some actual bounds. But I guess the thing I was going to say now, just to address Mateusz's question, is that here the diameter is some kind of measure of how hard this learning problem is. Like the bigger the diameter of the MDPs you allow, the harder it gets to learn it, because if you make a mistake, it might take a long time for you to be able to come back. And then the decision and estimation coefficient, as far as I understand, is sort of a more general notion of, which is kind of, you can think of it as analogous to the diameter for the case of MDPs. So it's something that you would put in a regret bound that measures the difficulty of a certain hypothesis class, but I think it's defined for basically any class of hypotheses. So it's a very kind of universal measure of the hardness of a certain hypothesis class. So yeah, maybe that gives a rough idea of how that fits into this picture. Any other questions? Okay, so maybe we're 10 minutes over, so maybe we can stop here and continue next week.